Okay, so there's also the integrated rate law as well. So the rate law basically can be integrated since we're talking about, think about it. Yeah. We have rate equals delta concentration over delta T. How many of you guys have taken calculus already? That many?
No, not yet for me.
Not yet. Okay, so I'm going to introduce you guys to a little bit of calculus, just a little bit, right? So pre-calc, that'll work. Okay, so part of calculus, you do what we call an integration. So this delta concentration over delta T is the change of concentration over time. You can also do this in calculus. So we will go, the rate is going to be equal to the derivative of the concentration, which represents that change of the concentration as a function of time over the change in time. Okay, so when you take the integral of this equation, right, you're going to get the integral is it's like the inverse of a derivative, and you're going to end up with various let's see. So it'll be the integral of the equation over a function of time is going to equal the time, and then you take the integral of both sides. Okay, so when you take the integral of this function, you're just going to get a constant times time. Okay, and then, oops, sorry. Let me fix this. That should be a C, not a T. Okay, so you take the integral of both sides, and then you're going to get a function as a function of time. Now, this integral allows us to sit there and look at the rate law in terms of the concentration as a function of time. Okay, so it allows us to sit there and put time into the equation itself and use that time rather than just looking at it in terms of just the experimental analysis. Okay, so we're able to sit there and establish a function once we get that rate law established. Okay, so let me show you what I mean without having to go into too much calculus, because we're not ready for that yet. Okay, so the integral for the rate law is going to be based upon the rate being equal to K and the concentration of A, and then not, meaning that it's not a function of A at all, right? Because A to the 0 power is just going to be 1, right? You guys remember that? If you have X to the 0 power, that equals 1. Yes, no, maybe?
Yes.
Okay, good. Okay, so that's going to be the same case here when we have a 0 order reaction. So in the case of a 0 order reaction, you're saying that the rate is equal to K. And when you take the integral of the rate equal to K, so you'll take the integral of this. And so basically you're saying that rate dt equals K. DC. Okay, so if you take the integral of this, of both of the sides and everything like that, you end up with K T equals, and then you have this basically will be the concentration. This is going from A to A naught to AT. Okay, so then you'd end up with just this part right here. Okay, so again, we won't go into the how you go about it, because basically when you take a derivative, it represents the area under that curve. And so when you take the integral, you're looking at the function of that curve. Okay, and so when you break it down, you get a nice linear reaction. So if you think about this, your concentration is changing. As your concentration is changing, this is here is going to be a constant. This is going to be your starting out concentration. And then this is to whatever value T it is, right? Whatever at time T, what that concentration is. And so that's just going to be equal to KT. So then if you graph this, you're going to get a linear equation, right? Because you're graphing it as a function of time. So let me show you what I mean. Okay, so clear. So this is a zero order reaction. So it's perfectly linear, right? Where a first order reaction has like an exponential curve associated with it. Okay. So when we talk about a first order reaction, this guy is basically taking in consideration the derivative again, where you bring the T over on this side, and then you have this as a function of A, and so you take 1 over A, and then you basically solve the derivative. When you solve the derivative for the first order reaction, you're going to get this integrated rate law. Okay, so this is for a first order reaction. Okay, so this is going to be the natural log of the concentration of T over the initial starting concentration is equal to K times T. So it's a function of time again. So if we go back to that equation, I mean the graph before, so this is the example of that, the graphing of that function. Okay, so that would be a first order reaction. This is going to be your second order reaction. Okay, so first order reactions are often used for when we're trying to determine half-lives. So when you're trying to figure out half-lives for like radioactivity, or half-life of a drug, or half-life of proteins being turned over, right? And so the way that you calculate the half-life on that is using that first order reaction. And then here you're basically saying, should put this in here first. We're saying ln T, ln A over A naught. So if you think about half, so you're calculating that half of a reaction. So if you calculate the half of a reaction, you'll get log of 1/2, right? So you're initially, this is what you have, and then this is what you're going to be left with. So if you lost half of your product, ln 1/2. So if you get ln 1/2, then what is the natural log of 1/2? Are you there?
I got negative 0.693.
Okay. So it's going to be that negative 0.693. And if we go back to our equation here, oops, wrong way. So
Would be positive.
and that's a negative value. So then that negative is going to be positive, and then you're just going to get, when we do this equation, you're going to get 0. Oops. So you're going to get 0.693 over K is going to equal RT. And that's going to be T for 1/2. Okay, so that's basically letting us know that when we get to that point where we're reaching half of our concentration, that's going to be the time associated with them. Okay, pretty simple. Ish. Okay. Okay, so cyclopropane undergoes decomposition by a first order kinetic reaction. First order kinetics with a rate constant of 9.20 times 10 to the minus 3 per second at 500 degrees Celsius. How many minutes will it take for it how many minutes will it take for 80% of the original cyclopropane to decompose? Okay, so if you look at this, we're going to use this equation here because we know that it's a first order reaction. They're going to be using the equation down here. Can you guys see my green and this beautiful blue background?
Yeah.
Okay. And so it says, how many minutes does it take for 80% of the original composition, the original cyclopropane to decompose? So in other words, we're going from 100% down to, so that we're losing 80%, right? So if we do that, if you're saying that your initial was 100%, and then you're decomposing so that you lose about 80%, then what is the percentage at time T?
Would be 20.
20%. Okay, so we'll have a ratio there. So you'll have what, 0.2, right? So ln 0.2 is going to equal negative KT. And then you just solve for T. So, and we know what K is. So we plug in our value for K. Okay. What do you guys get? And this is going to be T in seconds, right? Are you there?
I got 174.9.
Okay, so 174. You said so.
Yes.
175.
Or 120.
175 seconds. So if we change that to minutes,
Divide by 60.
60 seconds
So
equals 1 minute.
3 minutes.
So 3 minutes.
I rounded a little too much. So it'll be 2.9 if we have 3 sig figs. This guy's 3 sig figs. This guy's 3 sig figs.
Oh, okay.
2.91, right?
Yes.
Okay. Piece of cake.
That one was.
Okay, so I hardly hear somebody.
That one was.
That one was. Okay. You made it back in. Okay.
I was waiting for like an email of like, hey, come back. So I was like,
Oh.
let me try.
You know me, I don't email. Okay. Let's see. Come on. Okay, so this is an example of the half-life, right? So it says, how many minutes will it take for a reactant concentration to drop from 0.150 molar to 0.0300 molar for a first order kinetic reaction? A half-life is 8.50 minutes. Okay, so now they're giving us the half-life in this case. They're saying T1/2 equals 8.05 minutes. Now we know that this is going to be equal to minus ln concentration of, or we should say, when the concentration of A over A naught is going to equal 1/2, right? So I'm going to say, just write that in here. A is 1 and A naught is 2. Because we know that's what T1/2 means, right? The half concentration. And then that's going to be divided by K, right? So here we have an opportunity to figure out what K is, right? So then what is going to be K? Solve for K. K is going to be equal to minus ln 1/2. So divided by 8.50 minutes. So then K is going to equal, that's 0.693, if I remember correctly, over 8.5.
I got 0.0815 or 0.081. Or technically 0.082.
So, well, technically, so this again, we assume this is going to be 3 digits because it'll be 0.000, 0.000, because these guys have 3 sig figs here. No problem. I'm being lazy, my bad. So 0.0, you said 815. That's going to be 1 over minutes. So that's going to be our value for K. So now that we know our value for K, we can sit there and figure out how many minutes it's going to take for us to go from 0.50 to 0.0300, right? Because then all we need to do is just plug in for our LNA. We have LNA equals A at time over A naught. That's going to be minus divided by K, and that's going to equal T. So then we just plug in the values that we have now, since we have everything. So we'll have 0.0300 molar divided by 0.150 molar ln negative divided by our value for K, which is 0.0851, or sorry, 815.
Dr. Henry, isn't for your initial equation, isn't it the A naught over AT, not AT over A naught?
Well, when you subtract it, yeah, it's going to be your, let's screw that up. No, it's AT over A naught. But when you subtract it, it's going to flip. So.
Okay, I had it written wrong. Sorry.
And that's going to give you
I got 19.7.
Okay.
That'd be minutes. Yeah, minutes.
19.7 minutes.
Yes.
Okay. Piece of cake.
Yeah.
Okay. Okay, so a second order reaction. So this would be the rate for a second order rate. So when you do the integral of this, you'd end up with this equation. And so again, here you're just gonna use the fact that since you guys haven't done calculus yet, just take the fact that you have this equation. So this would be the second order rate constant. This would be the integrated constant. Integrated always puts it as a function of time, okay? So how do we use this? It says use the correct integrated rate law to calculate the time in seconds for the initial concentration of 5.0 molar decreasing to 1.00 molar using the following rate law. So the rate law was 1 over concentration of AT minus 1 over the concentration of A naught. It's going to equal KT. Okay. So in this case, it's just going to be a plug and chug type of equation. So you plug this guy in for your initial concentration. So it's 1 over 1.5. And then you have 1 over 1. That's going to equal and then here, this is our value for K, since they gave that to us. So then, so we'll have divide that by our value for K. So that's 0.200. And then that's going to equal T.
Just confirming that that's not a given all the time. You may have to solve for K at times.
Yeah.
Okay, so it just kind of depends. It's not like a super constant.
That's right.
Okay, cool.
Okay, so you end up with like 1.67 seconds. Okay, good, bad, ugly.
I'm sure we'll make it ugly, or at least I will.
Don't worry, we're getting there. Okay, now sometimes we got to do this graphically, right? And but if we sit there and we look at our equation, we do it graphically to try to determine the rate law. So there's a couple of ways that we could sit there and do it. Because let's see, so if we look at our remember when we did our rate constant, or say our integrated. So to calculate the rate constant using graphical method for a first order reaction decomposition. So they're letting us know that this is a first order reaction. So we can sit there and graph this information to determine our rate constant, because we know that our first order reaction is going to be ln A T over A naught is going to equal KT, right? So we can also write this as ln A T plus A naught. Oops, sorry. Minus, my bad. Minus ln A naught. You guys remember that from exponents and logarithmics? Yes, no, maybe?
9.
Okay, well, you want to brush up on
yeah.
that. Yeah, definitely brush up on that. Okay, so then this guy is going to be a constant value, right? That's going to be a constant. And if you guys remember, this guy is going to be a variable, right? It's going to be changing. So I could say AT ln AT equals KT. I forgot minus here. Plus ln A naught. You guys remember what is the generic formula for a line? Y equals what?
MX plus B, right?
Yep, y
Yes.
equals mx plus b. So if we look at our this equation here, we basically have a formula for a line, right? So where our minus k is going to represent our m, and then this is going to represent our b, and then the ln y is going to represent our, I mean, the ln a to the t is going to represent our y. Are you with me?
Yeah.
Okay, so we can sit there and plot it, right? So I'm going to go to Excel. And here. Come on.
Are we supposed to be seeing Excel, Dr. Henry?
Yeah, give me, I'm typing in the numbers right now. Sorry.
Oh,
So it's not showing up yet. 3.94. Okay. Okay, can you guys see that?
yeah.
Okay. So we're just gonna call this bracket A. Okay, so if we take the log of this guy, well, the natural log of this guy, then we'll have our y values, right? So we'll just go. So you type in ln, click this, hit return, and then we're just going to drag it down. Okay, so then this is going to be our y values, and these are going to be our x values. So I'm going to plot this guy, and I'm going to plot this guy. Oops. Sorry, this guy and this guy. And then I'm going to go insert, scatter. Okay. And then I'll do a curve fit. Maybe. Can you guys see my full thing now?
Yeah.
Okay. It's not going to let me see what I need to see. Okay, so I double click on the graph. If you go here, here, and this basically gives you all your chart options. So we could sit there and go with the title and the plot area and all of that. Let's see. Then I need to scoot over a little bit. Why isn't it giving me my series? Come on.
Don't you just do the plus sign for the extras?
Ah, there we go. I didn't know that. Okay, so you'll go ahead and hit trend line. And for some reason it's set up on linear, but I want to get more. So linear, more options. And then I'm going to put my equation in the curve. And then I'm also going to use display r squared value. So this lets me know how accurate my curve is. And so if you look at this accurate, the closer you are to 1, the more accurate you are.
Mhm.
Okay, so this is a pretty good accurate curve. So if we look at this, so that would be my A naught, right? Which is, if you look at a value of our A naught, okay, and then that is going to be, this here is going to be our negative
Okay,
K.
right?
Yep. So then K is going to equal it's going to equal 0.0033. And if I remember correctly, that's seconds. So it'll be, I'm going to erase this. It's going to be 1 over seconds. Okay. Do you guys see that?
Yeah.
Sorry. Oops. Can you guys see my, oh, there we go. Okay, so okay, and this is just basically showing you same thing that I did, and then here's the actual graph. Right. Okay, questions, concerns, Cash? No questions?
No.
Okay. Okay, so the next part is if we try to determine whether something is a first order reaction or a second order reaction or a third order reaction, right? So then we're going to be using all of the information that we know. So we know that a first order reaction, a zero order reaction is just going to be a function of time, right? So it's just going to be A minus A naught equals minus KT. Okay, so that's going to be a zero order reaction. A first order reaction is going to be, do you guys remember? Come on.
The ln AT over
Okay.
A naught
ln AT.
equals negative KT.
T down here. Over A naught equals negative KT. Then our next one is going to be a second order reaction where we get 1 over AT minus 1 over A naught is going to equal minus KT. Okay, so those are your three possibilities, right? So we want to try to sit there and determine what these curves are going to look like in all three cases, right? And so the way that I like doing it, it's kind of like I try to figure out the one that's going to give me the most linear explanation for each of the different scenarios, right? So we kind of set up each equation so that's linear, right? So if we do that here, we're saying, this is saying ln a t is going to equal that minus k t plus ln a naught. Okay. So this is what that curve is going to look like. So in this case, we're going to have our y being the ln a t. This case is simple. You're just going to have it being y equals, the concentration. So it's just what it is minus, equals negative kt plus concentration of A naught. And so then in this case, you're saying y is going to just equal the concentration. And then in this last case, you're saying that 1 over AT is going to equal minus KT plus 1 over A naught. Okay. Okay, so we're going to use the data that's given to us. So let's see. 240.
For the second degree, for the linear, it's negative KT plus.
Yep.
Okay, I just want to make
Yep. Okay. So let's plug this data in to an Excel spreadsheet. Let's do this. Okay, another window. Can you guys see my Excel spreadsheet?
yes.
Yeah.
But it's not going to let me do what I want to do. Control Z. Oh, maybe it is. That's not doing it. Okay, so I'm going to have to enter it. I thought I was going to be able to cut and paste. So we're going to go time. It's going to be 0 seconds, 60.00, 120, 00. Gonna get rid of that. Okay. $80, 240, 300. This is going to be my concentration of A, T. Okay, so then that is 1.00. This is 0.8. 0.667. Hope I'm missing one, so I'm sorry. 80. Okay, and that's 0.571, and this is 0.5, and this is 0.44. Okay. So now I need to do the one, because this here is going to represent that A is going to represent a zero order reaction. So this will be going to represent a zero order. This guy is going to represent a first order. This guy is going to represent a second order. Okay, so first order reaction is just going to be a normal. Second one is going to be ln A. And then the second order reaction is going to be 1 over A. So it's going to be 1 divided by. Okay. So here we're just going to plug in equals ln natural log. Oops. Come on. And then this one is going to be equals 1 divided by A. Okay, so I'm going to highlight both of these and then just drag them down. And that's going to give me my values. And then I'm going to graph these. So my time over I'm going to insert scatter. Okay, and then I'm going to do curve fit for each of them. So we're going to add the trend line to each one independently. So that's my, that would be my first order one, I believe. Then we hit trend line. Oops. Oops. Okay, so it's not helping me here. Okay, so trend line to that one. Okay, and then I'm going to go to trend line, more options. Okay, it's not doing what I'm supposed to do. Hold on.
Don't you have to pick a plot on the other lines?
Yeah, I do, but for it should work. Hold on.
Okay.
See, more options. Okay, there we go. Go to graph. You have to do each one independently though. So I want to display my equation, my R value. Okay. And then is that the one I just did?
I think so.
Okay, then that's my ln, more options. Oops. Come on. Okay. Let's go. More options. Here we go. Try this again. Okay. And then the last one is trend line. Oops, trend line. Crap.
You can undo it so that way it does it back.
Yeah, good idea. There you go. So the trend line. And then I did it again. Trend line. Cancel. Eventually, I'm going to get this. Damn it. Okay. So these were our three options. Okay. And let's see. The gray. Do you mind if I clear some of this out here? Okay. So the gray is our second order reaction. The orange is our first order reaction, and the blue is our zero order reaction. So if you look at our R values, that kind of tells us which one is more realistic, which one is the best. So which one is the best? Second order reaction. So the correct answer is a second order reaction. Because our R value is closest to 1, right? It's right at 1. It's perfect. So that means that the second order reaction explains the kinetics of this problem. Does that make sense? Are you with me?
So when you're just looking at the order of determination, you're just finding out which order is most appropriate.
Yeah. And so
Ultimately,
and you remember what that order means, right? So you're basically saying that if we're doing the rate, it says rate of this reaction is going to be K. And we could actually find out, we know what K is too, right? So our K is, in this case,
negative 0.0027.
oops. Sorry, no, it's remember it's the second order reaction. So it's going to be the 0.0042. So that's going to be our K. So the rate is going to be 0.0042. And then our initial is essentially 1. So this is going to be our K. And then we're saying that the concentration of, in this case, we're using A, is going to be squared, right? And so that's going to be our rate. But in terms of our integrated rate, it's going to be this equation here. Does that make sense?
Mm-hmm.
There.
Good. Okay. And you see how to use Excel so that you can solve it fast?
Yeah.
Okay, and you can also do this with Google Docs. Okay. Just don't make the same mistake that I made like 50 times. Okay, so let's go back. Okay, so your answer is a second order reaction. And then this shows you what a second order reaction looks like when we didn't take 1 over that value. This is what that first order reaction looks like. Okay, and so when we take that 1 over the value, you get a nice linear curve. Okay, so things that affects the that's going to affect our kinetics. It's going to be concentration, it's going to be temperature, and it's going to be state, and it's going to be the catalyst, right? So all of those things that we talked about at the very beginning, we're re-emphasizing. Okay, so because we know that temperature is going to be a factor, we have to take that in consideration. So the collision theory basically says that, you know, if you have things that are less concentrated, like you have 2 gases that are flowed in there, but they're very, very dilute, what is the probability of them finding each other and being able to collide with each other to form that reaction? Is it going to be high or is it going to be low?
Be lower, right?
It's going to be lower. So if I have a gas that's very, very concentrated, then it's going to be
Higher.
pretty high, right? Yes, no, maybe?
Yeah.
Yes.
Okay. Yeah, so if I increase that concentration, it's going to increase the probability of those guys colliding with each other. So if I increase the temperature, which is speeding up the molecules bouncing off the walls and everything, is that going to increase the probability of them finding each other and interacting?
Yes.
Yes. Yeah. Right. So when you guys did your experiment with the glow sticks, what happened? As we increased the temperature, what happened?
The rate went up.
The kinetic rate went up, right? Okay, so this is the activation energy equation. And so this allows us to sit there and calculate the value for the kinetic constant, that constant. Okay, so then this equation here, ln equals, and E represents the activation energy, and R is the gas constant, or it's a which would be equivalent to the gas constant. 1 over T, and that's ln A. And so in this case, we're using R, we're converting it in joules, Kelvin, moles, instead of using 0.22 ATM liters, right? So a joule is going to be equivalent to ATM times liters, okay?
Is that that's a constant that we're going to be using, or is that just for this specific?
No, that is a constant that you're going to be using. But that constant, this constant here is the same thing. It's the same thing as the 0.0821. Only thing, this is in joules
You just
instead of
converted. Okay,
yeah,
instead of ATM.
ATM liters over moles Kelvin. And that should be a capital K. So Kelvin, okay?
R should be a K.
Yeah. Oh, no. R should be a R, but this should be a K. A capital K instead of a lowercase k. And then the way I write it, I always write it moles, so I don't think it's kilomoles. I always write it moles Kelvin. Mr. Bella, right? So I don't mistake it for something else. Okay. And we know that this guy, that's going to be a constant. Okay. So here, our K is going to be a function of T. So if T changes, K is going to change. I know you guys thought you were getting away from math. Okay, So here we have, so this basically just shows you the activation energy. So the activation energy is the energy to get over the hump, that potential energy, so that you can get to the reaction, so that a reaction can occur. If you don't get over that hump, then that reaction isn't going to occur. Okay, are you with me?
Yep. Yeah.
Okay. So calculate the activation energy for a reaction with a rate constant of 4.5 times 10 to the minus 5 molarity seconds at 195 degrees Celsius, and then at 3.20 times 10 to the minus third molarity per second. I mean molarity second at 258 degrees Celsius. Okay, so if we look at our equation, so it was, go back to our equation. So it's L and K going to equal minus EA R times 1 over T plus LNA. Okay, so if we sit there and we look at this equation, and I copy this equation, LNK, I'm going to show you a little shortcut to doing substitutions and plugging things in real quick. EA over R. One over T. Okay, plus ln A. So if I say this is K1, R is a constant, EA is always going to be the same. The only thing that's changing in this case is T. Okay, and then this is going to be K2. So the only thing that's going to be changing here is T. So if I want to get rid of the A here, I would subtract this equation. So I'm going to take this whole equation and I'm going to make it a minus. And then I'm going to add the two equations together. So I'll get ln K1 minus ln K2 equals EA minus EA over R 1 over T1 minus 1 over T2. And these guys are going to get rid of each other. Okay. So then I can break this equation down even further, make it a little bit easier to kind of wield. And just because I know the laws of natural logs or logarithmics, so then I could just say ln K1 over K2 equals negative EA over R T1 minus T2. Okay, so now I can just plug and chug, right? Because I have my K's. This is my K1. This is my T1. This is my K2. This is my T2. The only thing is that I have to change my temperature into Kelvin. So I need to add 273 to each one of these. equals what? 8, 6. So 468 Kelvin. And then this guy is going to be plus 273. So then that's 1, 3, 5. So 531 Kelvin. Is that correct? Or am I making stuff up? So then I just plug it in, and then I'm also going to solve for EA. So, there you go. EA equals ln K1 K2 divided by, that should be R, one over T1 minus 1 over T2. And let me not forget my minus. So then I can just plug those numbers in. So my EA is going to equal, so we know that R is, so it's minus 8.314 joules moles Kelvin. So my K1 is going to be 4.5 times 10 to the minus 5 divided by 3.2 times 10 to the minus 3. All over 1 divided by 468. Minus 1 divided by 531. Okay, so what do you guys get?
3946.58.
39. Okay, I don't quite get that.
Did you say that again?
I said I don't quite get that. Let me do the calculation. Not the value. 2. Oops, I forgot my ln. Sorry. So that could probably explain. ln.
So I got a very large number now.
Okay. Like how large?
59. Five nine two 928.
Okay, so I get 137. I mean 137,945. And so yeah, it'll be 100. How many sig figs? 3 sig figs, no, 2 sig figs. So 140 kilojoules in terms of energy. This is what I get. Equals 1, 3, 7, 9, 4, 9 joules. Per mole. Or sig figs 140 kilojoules per mole. Okay. So this is one way of doing it. We could have also used the original equation. And if you have multiple data points, you can sit there and do the graph and calculate it that way. So here we have 2 data points. Technically, we could have done the same thing, calculate it that way, and then gotten the curve. Because if we look at our equation here, this is, where's our original equation? Right here. So our original equation right here. So we can set it up in a line format where this is going to represent our y, this is going to represent our x, and then that's going to be our slope. And so we're looking at the slope. We'll solve for our slope, and then we'll have to multiply it by r to just get that EA. Okay.
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 Okay. So this is just well, this is just showing you that curve in the case using Excel. Okay. So so basically with kinetics, your balance equation isn't going to do too much determining how fast a reaction occurs, right? And part of that is because there's a lot of times there are intermediate reactions that aren't shown. And that's the reason why we don't take that in consideration, that balanced equation in terms of the kinetics of the reaction. Now, if you could break it down into those intermediates, you could sit there and use it as means of figuring it out, right? But you'd have to know all of the intermediates. And then in that case, then the reaction kinetics could be used to sit there and do the calculations. Okay. And for this, you guys just kind of need to know this in the back of your head. You guys, when you get into your more specialized fields, you'll start talking more about those intermediates. Okay. And then how to determine those intermediates, particularly in organic chemistry. Okay. So, and then the other thing is that the type of reactions that you typically have, you're going to either have a unimolecular, you're going to have a bimolecular, you're going to have teramolecular. Basically, one molecule, 2 molecules that are going to be determining your reaction, or you're going to have, 3 or more, so 4 in that case. Okay. Your rate determining step is So sometimes you have a reaction that occurs, but it's going to be dependent on another reaction, right? So you always use the slowest step as your rate determining step, because you're not going to be able to make anything until you get that slow step taken care of first. Okay, and this is very important in terms of the biological aspects. So those who are planning to go into like pharmacology and drug design, you know, so you want to sit there and pay attention to that quite a bit. Okay. Let's see. Lastly, catalysts. So catalysis is just basically the use of a catalyst to help a process, right? So catalysts can be organic molecules, they could be inorganic molecules, they could be enzymes. And so it's anything that's basically going to speed up the rate of the reaction. Okay, and the way that they essentially work is that they orient the product so that they orient the reactant so that it's allowed to sit there and react faster, or it can. And so that orientation basically affects the activation energy, and so it lowers that activation energy. And I'll show you a graph of that here in a second. And so catalyst can be classified as homogeneous. Basically, it's going to be a enzyme in solution, or it can be something that's heterogeneous. So in the case of a metal phase that's added to like a solution. Okay, and this is a figure of a catalytic reaction. So this is what the reaction would normally look like. So it has very high activation energy. And so with the catalyst, we drop down that energy so that it takes less energy to sit there and get over the hump, right? So it's kind of like if you have a hill and you're pushing a car up the hill, right? And then you realize there's a tunnel that goes through the hill. Are you going to continue pushing the car up the hill, or are you going to go through the tunnel?
Go through the tunnel
Why?
because it's less energy.
It's less energy, okay? And so that's essentially what a catalyst does. It makes that tunnel through it so you're not using as much energy, okay? Simple?
Yeah.
Okay. So things that you're going to need to know about catalysts, just know that generally that it lowers the activation energy, right? That's what you're going to need to know. Things you need to know about the mechanism, so that you can have intermediates, and those intermediates can affect a reaction. And that's the reason why we have to determine things experimentally, because a lot of times we don't know those intermediates, okay? And if we did know those intermediates, we could actually use the stoichiometry and a balanced chemical equation to sit there and calculate. Otherwise, we only can do it experimentally, okay? And then, what was the other thing? Oh, what determines the rate of a reaction? And that's always going to be the slowest step. So if you have a multi-reaction experiment or process, then the slowest step is going to determine the rate of what's going to be produced. Okay. Questions, concerns, Cash? Oh, real quick. It's not up yet. I'm working on your lab, but what you guys need to do with your lab, so you have 3 eggs, and you should have 250 ml beakers.
Uh-huh.
How many 250 ml beakers do you have?
I think we only have one.
You only have 1? I didn't give you guys 3?
I'm gonna have to go look.
Okay. Check to see if you have 3. Okay, so because you're going to use your 250 ml beakers, you're going to put your egg in it, and then one of your eggs, or if you have like little cups, little plastic cups or whatever, you can use those as well. And one of your eggs, you're going to put, you're going to take the egg, you're going to weigh it, and then you're going to put it in just water alone. And the other egg, you're going to take it out, you're going to weigh it, and then you're going to put it in water with 15% sugar.
hold on.
Okay. So you're
So
gonna make a sugar solution that's 15%. Let me write this up on the board. We have egg 1 and water. Egg 2, 15% sugar. And then egg 3, you're going to leave it in the solution it's in, but you're going to weigh them all. So weigh all your eggs.
Dr. Henry, how do I weigh my egg that is completely destructed in the vinegar?
It's
Do I
okay.
just
So when
scoop
you
it
say
out?
it's completely destructed, because technically they all should be, your shell should be off of them completely, pretty much, right? And so all you're going to do is pick up that egg and then put it in there. If your egg actually cracked and the yolk just went out, so then
Yeah.
what I'm going to have you do is you're going to keep one in water and then you're going to keep one in sugar. That third egg is going to be the one that's in vinegar. That's going to be remaining in vinegar. You're not going to worry about that.
Yeah, this is the
Are you
one
showing me
egg.
now? Hold on, let me look. Okay, so one of them actually just broke open completely.
Yeah, because it's super soft.
Okay. Okay, so then that case, yeah, so then you're gonna have to, that one is no good. So then you're just gonna do the first two, and then the last one is just keep in solution.
Can I leave the broken one in solution and then just do
Yeah,
like
that's
a
true. That's true. You could do that.
afterwards just subtract the weights of everything?
Yep.
Okay, like the weight of the glass.
You could do that. Yeah.
Okay.
Okay.
So the third egg we keep in the same vinegar, so we don't have to weigh it, or do we weigh it and then drop it back in?
Yeah, you're gonna weigh it and drop it back in. Okay. And then you're gonna keep these guys keep them that way until next week. Okay. And then we'll do the last part is do the calculations, because then you're going to reweigh the egg in all three cases. Okay. Okay. Any other questions? Anything else that I forgot to tell you?
I have a question about the eggs, Dr. Henry.
Yep.
So you would put 3 eggs in vinegar, and then one of them would be in water and the other one with the sugar? Or
That's
do you
right.
just, oh, okay.
Okay, so you should have already put your eggs in vinegar, and that should have removed all of the shell off of it, pretty much. And so you should have basically all the shell removed, because that's what the vinegar is doing. It's acting on the calcium in the egg, and it disintegrates it, or puts it in solution. And then, so after you've done that for a week, then you're going to move it to 1 egg goes into water, 1 egg goes into your sugar solution, and make sure your sugar solution is dissolved. Otherwise it isn't going to work out right. You want to make sure you mix it well, kind of like making Kool-Aid. Okay. And even if you have to heat it up. Okay. And then you're going to have the one that stays in vinegar. Does that make sense, Selena?
Yep, that makes sense.
Okay. So then next week, what you guys are going to do, you're going to weigh it again. Right? You're going to weigh your egg again. And so then we're going to calculate the osmotic pressure on both sides of the egg. Right? And it's going to be important that you guys, you're basically keeping it at whatever room temperature you are, right? And you guys remember how to calculate osmotic pressure?
I have to go back through the slides. Oh, hey, that's another thing. Can you put the slides back up?
Yeah.
Okay, because I still don't have the.
Oh, I can send you the copy of them like I did earlier. I did it earlier. You probably weren't on yet. So
Okay.
File. And then I'm also going to put, see if it'll let me do both. Nope, it's not going to let me do both. Okay, I'm also gonna put Wednesday slide up too, slides.
Download. Save. Thank you.
Okay, Wednesday slides are up,
That's 13.
13 and 14. So basically 13, 14, and 15 all deal with equilibrium. One is just gonna be general equilibrium. The next one is gonna be dealing with acid-base equilibrium. And then the last one is gonna be special case. And so we're gonna kind of combine those in one.
Were you putting up the equation? Or are you gonna have us search it out?
I'm gonna have you guys search it out because you guys should know it by now.
Okay.
Okay. Okay, so did you guys all download the slides in the chat?
Except 15. Sorry, there you go.
Okay, so we're gonna do a very condensed one, very general first, and then I'm gonna give you specific cases. Okay, and then I'll kind of explain that.
And then do you want us to start on our wine?
Yes,
Like,
so
Just the
what
fruit?
you guys, for Wednesday, you guys are gonna need sugar. You're gonna need 5 pounds of sugar.
Holy.
You'll get a
gee.
5-pound bag of sugar. Well, you're making a 2-gallon thing of wine. You need enough to sit there and sustain the yeast and everything. So
I didn't know. Well, I didn't know there was that much sugar in wine. Holy crap.
Yeah. Well, it isn't anymore because that sugar is being converted to alcohol.
Well, yeah, but I'm just saying, like, initial startup, like, it makes sense though. But
Okay, and then you're gonna pick out your fruit of choice. And so I will be putting up a table of fruit. And so usually it depends on the fruit that you have, but you want to get anywhere from 2 to 5 pounds. If you have a little more fruit, that's okay, you know. So the more fruit you have, the more flavor that wine is gonna have. But 2 to 5, no more than 5 pounds.
I have a question, Dr.
Yep.
Henry, for the wine, because you know how some say like spices. Is that an
Mhm.
option? Do we add when we put the fruit in, or
Yeah.
is that like later?
That's an option. Yeah, and you
Would
can
you
do it. Well, you
recommend
want to
that
be
or no?
careful. Well, you want to be careful about what spices you add early because certain spices will inhibit yeast growth. Like cinnamon.
Okay.
Cinnamon is okay. Actually, yeast kind of like cinnamon. They actually grow pretty well in cinnamon. But there are
That's
other
what
spices.
I was leaning towards.
Yeah. There's other spices like nutmeg will actually affect yeast growth. It
Ugh,
actually slows it down, and so you want to be careful about when you have those.
nutmeg is nasty. That. Ugh.
Okay.
All right.
Okay, so I have another class. So I will see you guys later. I'll see you guys on Wednesday. And I'll be fixing your homework assignments this week. So, and they're also going to be smaller. So, I know you guys like doing a whole bunch of homework assignments to kind of get your feet wet. So they're going to be a little bit smaller than they normally are because we're in crunch time now.
Okay.
Okay.
Dr. Henry,
Yes.
I was wondering if I could schedule, since I wasn't able to pick up the wine and the kombucha kit
Yeah.
on Saturday.
So actually, Cole, I gave you his email. I actually sent you an email with his email.
Okay.
Did you get it?
I don't think.
So I'll give it to you. I'll put it in the chat right now. So contact Cole.
Dr. Henry.
Yep.
How do we know what we got?
What do you mean by
was
how
gonna
do you
ask
know what
that
you
too.
got?
Like, how do we know if we got wine or how do we know if we got kombucha?
Okay, how old are you?
21. Well,
You're
no, I'm not
21?
21. I'm 23.
Uh-huh.
But I
Okay,
feel like
I need to see ID. And then I'll let you know what you got.
Oh my God.
What was that?
Okay, I'll show you my ID
Mhm.
next class.
No, you can just show me in your thing right now. I'll just pull it out.
Can I
Work
do
it
that
out.
too?
What was that?
Can I do that too?
Yep, you can do that
So if
too.
we show you our D, you will tell us what we got?
Yeah,
Oh, okay, hold on.
okay, let's see. Let me pin you, Kayla, so I can actually see it. Let me stop sharing. Okay, so you turn 21. You got to scroll down because I see your height and your
Can you see
okay
it?
date of birth 20 2020. Okay, so you turn 21 when? The 20th? You turned 2020, right? 8. So you turned last summer. Is that correct? Let's see.
Taylor, you're
I
muted.
see
bud.
yours. I see Kayla. So let me see yours, Kayla
Oh,
again.
last month. Hold
Last
on, let me
month?
find my birthday. Oh yeah, my
There we go. Okay, so that's what I need to see. Okay, date of birth. Okay, so yeah, you're good. You're good. Okay, so you guys will have yeast added onto both yours. So I already put yeast in there. Otherwise, you would be using SCOBY.
Oh,
And then I'll know because when you guys go to turn in, you got to bring a sample of your wine to me. So in
So
your
you're gonna be grading after you've tested all of our stuff, right?
Exactly. That's
All
exactly
right,
how
y'all.
it works.
Higher alcohol content. Dr. Henry would be very generous.
damn, I'm excited. I got wine.
Yeah. So technically you have both and you have the option. You can do SCOBY or you can do wine. But if you tell me you do SCOBY and it tastes like wine, we're gonna have to talk about your procedure there. There's obviously something wrong. Okay, so I'm gonna let you guys go. And so get your fruit and your sugar ready for Wednesday, because we'll start it on Wednesday, because it takes a while to go through the fermentation process. And
5
you're gonna
pounds
be,
of sugar, right?
what was that?
5 pounds of sugar?
5 pounds of sugar, yeah. So
2.5 pounds of fruit.
Yep. 2.5 pounds to 5 pounds, yep, of fruit. So it depends on how much fruit you want, how fruity you want it to taste. And you can use any fruit. It works with anything. Lemons are a lot harder, and you'll definitely have to get rid of the rind, or citrus fruits in general. Or you can use juice, fruit juice, if you want to go with the easy route.
Just use fruit juice.
Okay?
Awesome.
I'll see you guys on Wednesday.
Okay.
Okay. Have a good day.
Bye.
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 Bye.